YouTube. By the way, that's always no matter how many times you've heard yourself speak, making something available on YouTube makes one very self-conscious. So I do that for you despite my better inclinations of not doing that. Pretty frightening. So anyway, what we're going to talk about today is we're almost nearing the end of our discussion of the second major piece of the course, which is this topic of concurrency. Hopefully you know we're talking about concurrency right now. If not, you have some catching up to do. And in any case, what we're going to do is we're going to talk about a pretty famous synchronization primitive today called the semaphore. That's highlighted here in text. So it's an old synchronization primitive. In fact, when the fabled Edsger Dijkstra, whom we've talked about before in this class, came up with he realized, of course a lot of people realized this, that you needed something like locks and something like condition variables. But for Dijkstra, when he realized it, he said, oh, I need to have this synchronization primitive and I just want to have one, and I'm going to call it a semaphore. And semaphores are used for signaling is why that name came about. And so in the early operating system that Dijkstra wrote with his colleagues over in the Netherlands, they used the semaphore inside the operating system to make sure that when concurrent things were happening inside the OS, that it worked. And of course, for this work and for other work, Dijkstra won the Turing Award, big award in computer science. And what was also kind of interesting about that is if you read his memoirs or his early papers, he reflects on it, and it's really, he was a guy coming from the world of mathematics, as were a lot of his colleagues, and for certainly a lot of people that entered when computer science formed, a lot of people that went into it first were math. And one thing that I think Dijkstra writes about very nicely, if you ever do get a chance to read about him, or frankly, if you take the graduate operating systems course, you'll certainly read papers that say this sort of thing. He talks about the realization that building computer systems is actually challenging. Like that people didn't know that at first, that it would be really hard to build a working system, and that you have to think about how to build systems, and you have to have a principled, structured way of going about it. So it's kind of these things that people had to discover. Now you might say, well, it's obvious computer systems can be complicated and challenging, but it wasn't obvious at first, and in fact probably a lot of people in the more mathematical world would say, look, that looks a lot easier than this proof I'm working on, so maybe I don't have to worry about it so much. But it turns out computer systems are actually pretty challenging too, and so Dijkstra very nicely writes about that, and at some level switched his career from being a pure math person to becoming an early and influential computer scientist. So anyway, that's a semaphore. If you read about, again, the early forms of semaphores, all the language around them is also in Dutch. So we're not going to do any of the Dutch today, but if you read about it, well, I'll point out some places where you might see some differences in historical texts. So all we're going to do today is, well, that was a little history piece, so it doesn't get any better than that. The definition, we'll talk about what is a semaphore. And just so you feel comfortable, remember last time, what did I say? I said we learned about locks and we learned about condition variables, and that's it. You don't have to learn anything else. And that's absolutely true. You can build correct multi-threaded programs that have the variety of interesting synchronization behaviors that they need to have with locks and condition variables. But semaphores can act as locks, as we'll see today, and they can act as condition variables, as we'll see today. So they actually can act both ways. But there's so many classic problems that have been posed and then solved with semaphores that you may just run across them. So you kind of have to know what they are too, even though to be a functional and effective concurrent programmer, you wouldn't need to know them, right? You could just say, I know locks and condition variables, that's enough. So you have to know them. You might go on a job interview and they'll be like, what's a semaphore? Or use a semaphore to solve this synchronization problem. And if I hadn't taught you at that moment, you'd be cursing me. Unless, of course, you didn't know which class you were supposed to learn that in. And then you'd be cursing the school in general. So I might prefer that, perhaps. Okay, so what we'll start with today is then we'll start with simply defining this stuff. And then we'll just go through, like we've been kind of going through thus far, we'll go through a number of examples. We'll talk about how to use a semaphore to build a lock. Then we'll talk about how to use it to solve that fork join problem when you have a parent thread waiting for a child thread. That's the basic usage as a condition variable. Then we'll talk about how to build a semaphore out of locks and condition variables. So we'll see, how to build a working semaphore. And then we'll see one last thing probably today. I don't think we'll get to producer-consumer problem again, or the bounded buffer problem, but we will get to this new thing called a reader-writer lock. It's a more sophisticated type of lock, and we'll see what that is and see how to build it pretty simply, or at least a simple reader-writer lock with semaphores as well. Okay? Make sense? Okay, so let's start with the definition. Sorry, connection to internet slow means demos bad, means whole class suffers. Sheesh, look at that. Okay, in the meanwhile, pass this around. I'm going to show this, sorry. I'm going to show this on the screen as well as you handing it out, so you can just look at the screen and it'll slowly find its way to you. The definition is useful to keep out because as we try to solve the problems, we're going to have to kind of try to remember what a semaphore is. Okay, so that something happened there, which is good. Or maybe there's a C version of this. Sorry. Goodness, I don't know what is going on with this. It's so slow. All right. Well, let's just stick with this. It's on the board. So semaphores, I'm showing here. I guess I'll just sit here and talk about it. So let me describe it in two ways. There's two important routines that we're dealing with when we're dealing with a semaphore, and they're called wait and post. If you do look at really old documents, you'll see things like P and V instead of like wait and post. That relates to the original Dutch words that were used for these routines. You don't really appreciate how great it is that computer science became driven by people who speak English. Right? Every routine you ever call, every API you ever deal with is in a language that, well, at least most of you, from some of you, so your first language, others from overseas, not so much perhaps. But if you are English speaking natively, you might appreciate that. If you're not, well, maybe you're cursing that for having happened. But in any case, instead of some Dutch words like proberen and verhoeven or whatever those words were, we're going to use wait and post. And those are the two main routines we're going to be dealing with. Okay, and we'll look at what they do in a second. But there is one other thing we have to look at, which is that a semaphore always has a value associated with it. And this might remind you of how a condition variable, we often had a variable in the program that we'd be looking at in conjunction with a condition variable. That's kind of similar, but that was optional at some level. Here, a semaphore simply has a value, an initial value that you give to it. And of course, the routines wait and post are going to deal with this value in some way. Okay? So does everybody have a thing yet? A copy of this? It's all the way back there? Okay. So we have an initial value, and just keep out this sheet so when we look at the previous things. And then we have these two routines. And so let's understand, and this is kind of just the pseudocode of what these routines do. We're not talking about how they're implemented at this point. The waiting one is pretty simple, as is the post, actually. So what the semaphore wait operation does is it says, while the value of the semaphore is less than or equal to 0, in other words, while it's negative, basically put yourself to sleep. Okay? Simple. If it's not positive, put yourself to sleep. And then when you wake up, some other thread has woken you up at that point, then decrement the value. Okay? And then post is really kind of the opposite of that. And this should, again, remind you of some things we've seen before at some level. It's similar to other things we've seen. But in post, what we're doing is we're simply incrementing the value and then waking a waiting thread, if there is one, waiting. Okay? And each of these things, now you look at this kind of code and you're thinking, oh, multiple threads are calling into it. I might start to feel a little concerned. So somehow these are built in a way that whenever a thread is active inside of this routine, for example, well, you can view that as a critical section. So of course there's going to be some sort of locking or something preventing us from having multiple threads trying to, say, decrement or increment the value at the same time. That we'd have to implement this carefully so that each of these routines essentially does what it does atomically. Make sense? It's just pretty simple. And of course you have to, that's why I hand out the sheet so we can stare at it when we're trying to solve existing problems. So any questions about that? Yeah.
Is init just called once or across different threads?
So the question is init called once or multiple times? Usually it would be just called once to set by some initial thread that says this is what the value is.
What if you pass in a negative value to the init value?
You can pass whatever value in you want, and then you would have to determine on the usage of wait and post, is the correct thing going to happen, right? So we'll have to look at some code to answer that question. So yes, of course, how you set the initial value is going to determine quite a bit about how this code behaves, the code that uses the semaphore. Okay, any other questions? Kind of makes sense? I mean, this is just the definition. You kind of stuck with it. That's how a semaphore is defined. And so now the real way to make sense of this is to actually think about some example usages. And of course, one of the simplest usages is you can use a semaphore as a lock. And this is sometimes called a binary semaphore, as we'll see why. And of course, or you could call it a mutex, or you can just call it a lock. So let's look at some code that does that. No, that's not right. Yeah. All right. So I'm going to actually remove that. Hopefully you didn't pay too much attention to it. So let's start with that. Okay, so what are we going to do here? We're trying to use a semaphore. We're just going to use one. We're going to have to initialize it here in the main thread. And this is a program we've looked at before, so maybe that's why I'm not talking about it too much. But basically all it does is create a number of threads. Here is the loop that does that, and then it waits for them to complete. And each worker thread does our usual boring thing, which is our kind of minimal de facto synchronization problem, which is it updates a shared counter, okay, in a loop. It's not like a serious program, but obviously you know that this program to work correctly needs some kind of synchronization. So we're going to use a semaphore to do that. Obviously, if we're going to use a lock, we would simply initialize the lock here and then add a lock and unlock around it, right? That would be easy. So we're going to try to do the same thing, but we're going to go ahead and use semaphores. So we somehow have to initialize the semaphore to some value here. And then we have to do some routines up here, some semaphore routines, and there's only two. So you might have, even if you're guessing, you might have a pretty good chance of getting it right, which ones go where. So what some routine is called here, some semaphore routine is called here. So what we'll do now is you'll all think about this for, say, 3 minutes, talk to each other, figure out what the answer is, write the code down on some piece of paper you have, on the table, scratch it in blood on the wall for the next generation. Doesn't matter. Okay, I'm probably not encouraging some of those. But in any case, figure out what the answer is, and then we'll come back and talk about it. All right? So talk. And this is where I would play music, but I don't want to do that anymore. I decided we went too far last time. Now we must suffer in silence. So if you came in late, by the way, if anybody walked in late, you should have a sheet which has a definition of what a semaphore is on it. And now what we're trying to do is use the semaphore to solve this synchronization problem, this very simple synchronization problem of mutual exclusion, of making sure that when there's a critical section, only one thread is active within that critical section at any given time. All right, make some sense. Some people have some guesses. How many people have a guess as to what to do here? Some number of you. Okay, so, well, we know we have to call init down here. Let's ignore that for a second. Let's look first at this part of the code, which is we need to do something before we enter the critical section. And of course, we could put that just around the counter plus plus, or we could put it around the entire, in a more coarse-grained fashion, we could put it around the entire loop. Maybe we'll do that just for simplicity here. We have to put something here, and we have to put something here. Now, the way to think about that is when we're entering a critical section, there's one of two things we want to happen. One is we're the first thread to try to do this, or we're the thread that's trying to do it when no other thread is in the critical section, so we should be allowed to go ahead and proceed and enter the critical section, right? It's like a gate. That's what a lock is like. It's like a gate, and we should be able to get through the gate. But then we're making sure that the gate is locked, so that we might sometimes when we come up to this gate, this lock, we find it locked, and we have to wait a while until somebody unlocks it. Pretty simple. So then when we look at our definition, and we're thinking, well, do we use wait or post? It should be kind of clear which we should use, right? Because it's pretty clear in the definition of post that no matter what happens, you're never waiting for anything, right? You're incrementing a value and then you're waking somebody else up. So pretty clear if you're about to enter a critical section, you want to use the semaphore as a lock, you're going to have to call wait first. And then when you're done, you're going to be calling post. Okay? Does that make sense? It's kind of logical from the definition. So up here we're going to have something like, and I think, let me see if I did this. I don't know what is going on in the world today. Okay. This is me hitting a button and waiting minutes for something to happen. So I have the same kind of macro here, or wrappers, where we have a capitalized version of the proper routine. These are all seminit, wait, and post. You can do a man, look up the man pages. These are working routines on Linux-based systems. So I'll use a capitalized version in order to, and let's see what I called this thing. I called it lock. That's a good name. Very cleverly done. You're welcome for that. So we're going to put wait here, and we're going to put post here. That's the only thing we could do. We know we might have to wait when we're entering a critical section, so of course we're going to call wait, and then we're going to call post. What that doesn't tell us, though, is what to init the lock to, the semaphore called lock, what initial value to set it to. So what we should do there to understand what this initial value is look at the definition again and try to reason through what would happen if we use different initial values. So let's say we're coming in here. Let's think about it. We are the first thread to try to acquire this lock. Okay, first thread to try to acquire the lock. We come in. We want to make sure in that case that we don't wait, right? If the first thread that tries to get into the critical section waits, then we're probably not building a working lock at that point. So what does that imply about the value? It has to be greater than 0, right? Greater than 0 at first. That's what we know for sure. Then, let's say another, if you think about that, that means we have a greater than 0 value. And then what we want to do is, when we're done with it, we're going to, so then we decrement the value. Oh, sorry, let me describe this slightly more clearly, sorry. We come in, we're the first thread to do it. We want the value to be greater than 0 so we don't wait, and then we decrement the value. Okay, so the value was, let's say, n to begin with, n greater than 0, and then when we're through this routine and into the critical section, the value is n minus 1. Right? Does that make sense? So if it's n minus 1 at that point, what do we want to make sure is true about n minus 1 so that subsequent threads that try to enter the critical section actually get held up? Does that make sense? Did I state that in a clear way? Yeah.
That it's less or equal than 0?
Yeah, right. We want to make sure that after we've decremented it, that the next thread that comes in actually does get held up. So I probably could demonstrate this in a more direct way, but let's say the value is let me just do this. Where should I do this? Let's do it. Well, I kind of want to keep the definition up. You have the definition in front of you. You can all stare at the definition. So I'll go back to our notes file here and think about it like this. We have thread 1 and we have thread 2, and the initial value of the semaphore is, let's say, n, and then let's say thread where n is greater than 0. So then if I call wait, sorry, not wait, yeah, sem wait, we have to be careful how we refer to that. That's going to, well, it's not going to wait because n is greater than 0, but it's going to make the value, it's going to say basically n equals n minus 1, right? So now the value of the semaphore is just n minus 1. But we want it to be at this point that if thread 2 comes in and calls, before the lock has been released, if thread 2 comes in and calls sem wait, that it gets stuck waiting. So we want n minus 1, you can think of it to be, well, less than or equal to 0, so let's make it just equal to 0, which implies that n is equal to 1. Okay, so let's think about that. So n is equal to 1 means that the first thread that comes through checks the value. It's 1, so I don't wait, and I immediately decrement it to 0. And then let's say I'm holding the lock. Other threads come in, they find the value to be 0, they just wait. Finally, I increment it. I'm leaving the critical section. I'm that first thread. I increment it back to 1, and I wake somebody who's allowed to then continue and put it back to 0 immediately. Okay? Simple as that. So a binary semaphore is simply the case where you initialize the value to 1. And you just use wait and post exactly identical to the way that you would use lock and unlock. Okay? And we could, of course, look at the working code here, right here. So you can see wait and post, and then down here the init code is 1. And of course, we could even compile this. Like semaphores just work on Linux. They work inside of many kernels as well. So let's go ahead and compile it. Something like that. The compiler's calling out to the, who knows what it's doing. It's thinking. It's very complicated. I don't know what is going on today with computer performance. This is why computers are complicated. So while that's compiling, let's go on to the next thing. And well, of course, that's going to cause me all sorts of problems. Who knows what is that is doing?
It was doing this for me last night as well.
Oh, okay. We're you using semaphores?
No.
Okay. Yeah, I'm just going to stop doing that. So trust me that it actually does work, and I will show that. I was just doing it earlier this morning, so that's really irritating. Okay. So anyway, that is working code, and I'm always behind on doing this, but I try to make the code available so you can even download it and play around with it yourself if you're interested. On the handouts link on the page, the web page. Yeah.
So are we thinking that the semaphore implement the critical section is different from a lock? Like because you're trying to, like if it's using a lock, you're trying to implement a lock.
Yeah, it's a little bit bizarre. Kind of and we'll see this in a minute when we actually build it ourselves. We'll build a semaphore ourselves. If you didn't hear the question is like, hey, you're building a lock, but it seems like you kind of need a lock to build a semaphore, right? We need to make the critical section in there. There's a critical section just inside the semaphore itself. So that's true. I'll just kind of maybe defer that a little bit to when we look at this third piece of writing your own semaphore. But it's a little strange, right? It's like we're taking this very powerful primitive and building something very simple, which is a lock. And you need a lock to build the powerful primitive to use it in this very simple way. So it's a little bit strange, but like I said, it's useful to know about it, and yes, you might not always use it for that reason. Okay, other questions, thoughts? Everyone enjoying the weather outside? Very nice? Yeah, okay, good. It's like that in Seattle all the time. So anyway, what are we going to look at? We're going to look at the fork join problem. So let's go ahead and look at that. Pretty simple problem. And I'm just waiting for a backspace to work here. Yeah?
Like, is there any advantage of using a semaphore over like a spin lock or something? Or
In terms of like performance, how do all these locks differ?
I mean, in general, when you're calling in general, how are you going to use locks? You're going to call pthread mutex lock. You have no idea how it's implemented, and it's kind of painful to even find out, right? At some level, what you're doing is you're trusting the people who developed that lock. They know that if it's poorly done, it's going to make your code slow. So you're just kind of trusting them. There's sometimes you can influence what kind of locking is done. Like they'll let you say, oh, give some like hints to the library or whatever. But I think it's very generally hard to know. Really the best way to know is, hey, if I have some choices using this lock or that lock, is to measure and see. Here's my application. I tried this one, I tried that one under some workloads I care about, and this one's faster, so I'm going to use that. I think it's very hard to know anything more general than that. Okay, problem number 2, which we'll give you a couple minutes for, is the classic fork join problem. I'll leave it like this. You can see what the parent does. Parent creates a thread. We should, of course, first initialize a semaphore because we're going to use it for signaling. Then the parent calls something here, and the child, when it's done, it calls something here. So the problem, again, is for you, is what do we call where, and what value do we initialize the semaphore to? Okay, these are great, like simple forms of exam questions, by the way, and we are starting to think a little bit more about that exam because it's coming, right? It's coming, whether we want it to arrive or not, it will arrive. So this is a perfect kind of problem. Hey, what initial value should you give this thing, and how should you use wait and post to make this code work as expected? So let's take 3 minutes and figure it out. Maybe we do need some music, maybe. It's so much livelier in here. I'm trying to do something a little more classy than last time. Are we getting the answer here? How many people feel like they have the answer? save the music for next time then. All right, good. I found the right spot in the music at least. Okay, so somebody lead me through. What are we going to put here? This is a parent, and what is it doing? It's waiting for a child. So not surprisingly, what are we going to do? We're going to put wait. Child is done. How does it signal it's going to be done? Post. Good. And all we have to figure out then, as always, is the initial value of the semaphore, which is 0, right? It's 0. Because if we look at the definition, fatal bus error, that's a good sign. What is going on this machine? Wow, that is crazy. Okay, I'm going to log off of there. I guess we just won't run the code. Sorry. Where is this? I'm actually mildly organized about things like this. Okay, I'll just use my local machine, which is seemingly more working. And we'll just go from here, and we'll look at, yes, sure. Okay. So here's the code. We initialize it to 0. The reason it works fine is because of this definition. The reason we initialize it to 0 is because we want the parent, if it immediately does call into, right, the parent, a very likely code sequence is it calls init, it creates this thread which makes a runnable thing in our address space, but probably doesn't run it immediately. Often we'll just call wait right away. And the parent, when it calls wait right away, it better had go to sleep at that point. If it doesn't go to sleep, then it's not correctly waiting for the child. So that means that the value of this certainly has to be 0 or less. And 0 is the right choice here because we want it to be when the child does call post that it increments the value and then just wakes the waiting thread. So pretty simple. That's the fork join problem. So any questions about that? Does that make sense? And you can work through there's just 2 cases you have to think about here. What if the parent runs and calls wait first, or if the parent creates the thread and then immediately the child runs and does the post before the parent can do the wait. Those are the kind of races you might be worried about, but in both cases it works out fine because if the child does post first, it increments the value from 0 to 1. Then when the parent later calls wait, it'll see the value as 1, and then it won't wait. It won't sleep at that point. It'll just fall through, if that makes sense, right? So if the child runs first, the parents, when it finally does call wait, it won't wait at all. But if the parent runs first and calls wait before the child even gets to run, then it will wait, and then the child will wake it up at that point later, then the parent can run. So any questions about that? Yeah.
So what if you create a lot of children, and then how can you make sure that once a child process is done, it will not wake up the parent immediately? wake it up.
Yeah, great. So the question is a great question. The question is, for those who couldn't hear it, was, what if I have 10 children? I'm really into reproducing, and how should I handle this? How should I make it so that the parent waits for all of them? Yeah.
Add a value outside of the sample weight, and then the value should check the value of the value.
Well, you could do it that way. I mean, I think probably an easy way to do it is, what do you think?
Would you set it to -9? We had 10 child.
Yeah, so you can look at, let's look at the definition. What if we had the value is, however many children, there's a bunch of ways you could do it, first of all, right? One way you could do it is you could just have one semaphore per child and wait on all of them, and each child would post on a different one, right? So you could certainly do that, and that would work. And the question is, can you just set the value to something, extreme, right? Do people understand that suggestion? Let's set the value to say, let's say we know how many children we have, so we set it to some large negative value initially, and see if that works. So why don't we do this? Let's consider that before we take that question. Let's consider can we just set it, if we have multiple children, can we set the semaphore to some particular value and use basically the same exact code for just one semaphore? And why don't we take a break at the same time? So let's take our break right now. I was going to take a break anyway. Let's take a 3-minute break or 5-minute break, 2 minutes of which you should think about, can you just set the initial value to something to make it work for multiple children? Okay? So let's use the break. And I'll run some exciting music during the break, classing this place up. Let's see if this works. No, it's not the Fox music again. Does this work? No. Oh, come on, work. Oh, there we go.
Saw an image the other day. Because like apparently there's this video where it's like this guy just recorded like actual Fox calls.
Yeah.
So they did like a Google trend of that video, and apparently it's just spiked up recently. And that's like
Now people are actually curious. Oh, it lets people learn. All right. Oh, we can't read anything, can we?
you mentioned that like a binary semaphore is also called like a mutex. So
Yeah.
does that mean when we run like thread mutex, that's basically just the semaphore?
No, it doesn't. It just means they're functionally equivalent. Yeah, that's all I meant by that.
Question.
Yeah.
So like, it's called a con underscore t and a sem underscore t. What's with the underscore t?
It's like user-defined type. So it's like semaphore type,
Oh,
and that's just kind of historical. People do that.
okay.
Yeah.
I was
Why?
just
I don't know.
curious, so.
Yeah. All right, how we doing? Ready to go again? I said 5 minutes, but I didn't remember what time I said that at, and on top of it, I feel like starting again. So we're back. Sorry. Musical interlude brought to you by Beethoven, long since dead, but the music lives on. What symphony was that? Could anybody hear it? No, that's sad. All right, well, we'll start with the beginning again. To listen to some music. I don't know if this thing works. It kind of works, and then it kind of doesn't. Can you hear that? All right. You should know immediately when you hear it. If I say it's a symphony and you hear singing in it, you should know instantly. This you know, right? Everybody knows this. What is this? What? No. That's not. You should know like every Beethoven symphony. There's only 9. It's like the most famous music in the world. It used to be, apparently. You've all heard the Fox song. See, now I'm embarrassed for you. What symphony is it? You can guess, 1 through 9. 9, right. Last movement, 9th symphony. All right. Which is the best symphony? I don't know. Maybe it's a 9th, maybe it's a 3rd. Maybe it's a 5th. You know the 5th, right? What's the 5th? How's that start? Da-da-da-dum. Yep, that's right. Yeah, good. This is like the music. There's music people on this campus. They'd be horrified to hear this discussion. All right, so we'll have to review those symphonies a little later in class. For now, we'll just go back to our more pedestrian work of making code work. So the observation here was that maybe we could just use a single semaphore if we were solving this problem for multiple children. And the observation was, well, when we had one child, maybe we could set this value to 0. So let's say we were creating not one child but 5. What value could we maybe set this to? Yeah, maybe like if we were creating 5 children, maybe we could set it to -4. And let's think about that by looking at the definition again. It means, of course, when we first come in here as the parent, if the parent just runs immediately, it would say, oh, -4 is clearly, it's a low value, so I'm going to put myself to sleep. Great. And then as each child finished, it would increment the value by 1, right? So we have 5 children. We had set it originally to -4. So first child finishes, it goes from -4 to -3, then -2, then -1, then 0. And you can see each time maybe the parent wakes up, sure, but then it goes back to sleep because the value isn't high enough yet. And then finally the last child runs, makes the value positive. They're all finished at that point. And then the parent will be woken up and would actually return at that point. Does it make sense? So semaphores, that's why some people like semaphores, because they're really flexible like that, and you can do little simple synchronization problems with very few lines of code. Okay, so that's the semaphore is as a condition variable. Now we're going to look at 2 more examples. We're going to look at how to build one ourselves. I don't want that one. I want this one, hopefully. Yep. I called it a semaphore, just so we have a different thing. And I have a Z in my name. I've always been fond of the letter Z. So this is going to be the rough construct of our own semaphore class. And what we're going to use here is we're going to use a single condition variable and a single lock that we talked about before to implement these routines. Okay, simple as that. And what will we do here? We'll basically initialize inside of here. Here we're recording the value. You can see we also have a value associated with this. And we'll assume only one thread calls this initialization. And then what your task here is to write the wait and post routines using a condition variable lock and this value. Okay, does the task make sense? You have the definition of the semaphore in front of you, or you should, unless you already lost it or made a paper airplane. We could do that sometime too. We could make paper airplanes in here. I know a number of very good designs, so we'll talk about that later. But right now, what we'll do with the paper is look at it, and what in particular we're going to talk about is then how to make that definition go from pseudocode to actual code using a condition variable and a lock. And at some level, that will prove what I said to you is kind of true, which is that you can really do any synchronization problem with a lock and a condition variable, or some number of locks and condition variables. Here, you can build a semaphore, it turns out, with just one lock and one condition variable, and a related integer to track the value of the semaphore. So spend 3 minutes on that, and then we'll talk about it. You should just write out some code. Write out some code that solves just that implements wait and post. Okay, I'm going to play some music again. You're going to get stuck with, I realize now I should have to play classical music for this crowd because you're seemingly sorely lacking in training along these lines. Let's go to first big one, number 3. This may be distracting. We'll find out. Yeah, there we go. All right, I think Mozart's supposed to make you think better, but Beethoven probably does too. So you'll be smarter. I'm going to run this during the exam too. So. All right. I find myself, unfortunately, just wanting to listen to the music, which isn't that effective as a teaching tool, perhaps. That was Beethoven's which symphony? Third Symphony. What's also called what? Does anyone know the name of the symphony? Called Eroica, the Heroic Symphony. This guy hates symphonies. He's out of here. I'm kidding. So it's an interesting way to keep the enrollment down. Anyway, that's Beethoven's first really famous symphony, the Third Symphony. In any case, and we could talk more about symphonies later. So let's try to figure out the intuition behind how we implement weight and post with locks and condition variables. How are we going to use the lock in general? We know something about the semaphore, yeah.
To protect the value of this.
Yeah, we're gonna the kind of the routine itself. They're both gonna be kind of like critical sections, right? So we're gonna probably be calling lock and unlock as we enter and then leave these routines. So that's good. So then, what's the intuition behind how do we write the code for something like weight? Yeah.
You use that same while loop that's in our definition for value. And then inside the while loop, you use your condition variable to wait. And then at the end of your while loop, you lock, update the value, and then unlock.
Well, close. You don't have to worry about locking and unlocking so much, yeah.
Will we have to also do it for the checking inside the while loop? Because then they can both check if it's less than 0. Two threads can check if the value is less than 0, and then they can both have race conditions. So we have to.
Yeah. So let's just look what I did, and then that'll be probably the simpler way to do this. It's hard to talk about code. Code should be very simple. And all this code does here is it grabs and releases the lock around the major action of the wait, and same thing for the post. And all we do inside the while loop is do exactly what that, like you said, exactly what the definition says, is while the value is less than or equals 0, wait. Now, remember the property of the condition variable. We have to remember now something from a previous class, which is the condition variable, by its very nature, puts the calling thread to sleep and releases the lock, which will allow other threads to acquire the lock and do something, like, for example, wake you up, or it might allow another thread to come in here and also wait. That's okay too. And then only when it is awoken, it will reacquire the lock before returning and then recheck the condition and then do the decrement of the value. On the other side of the world here, the post does the exact converse. It locks, it increments the value, it signals, which makes somebody runnable but does not run them yet, and then it does an unlock. So it's almost like exactly like the definition in the pseudocode. It's just turned into locks and waits and signals. Right? So it's really easy to take a condition variable and a lock and build a working semaphore. And again, this is working code, and you could use it anywhere you use a semaphore. Now, quick question for you. What if, here I'm incrementing the value and then signaling, what if I did it in the opposite order? Does that change anything about this code? What do we think? Yeah.
If you wake up other thread before you increment the value, you can go into waiting again. Whereas you actually want to increment the value and then not wait for it.
Sounds good, but not true. Yeah. Yeah.
So since it's inside the bounds of the lock, the wait can't actually check the value of Z until it acquires the lock.
Yeah, that's right. This isn't a critical section, right? Critical section should mean one thing to you. If I have a lock and unlock, it means, and I don't do anything like a wait in there, it means this happens atomically. This stuff happens atomically. That's all a lock and unlock is doing. It's making all of those things essentially happen all at once to the program. So the order that I do things in there, if it doesn't affect if these two things are independent, and then I can flip their order and the code logically behaves the same, there's no timing I have to worry about. I don't have to worry about somebody getting in there between those two things because I've already guaranteed that these two things happen atomically. So it does not matter what order I do those things in here. Now, of course, up here, it might matter the order of when I check the value and then when I decrement it, because if I decrement it first, obviously it's a different value, so I'm going to be changing the behavior if I move this decrement above a while loop or something like that. But the only way code is active in here and running, or active in here and running, is if I'm holding the lock, which means that if I'm holding the lock, that I know I can play around and do things in whatever order. It doesn't matter. It doesn't change anything about the behavior of the system. Does that make sense? That's a really fundamental thing, right? That's what locks are doing, guaranteeing that a bunch of things happen atomically. The only time that isn't true, of course, is when you are kind of releasing the lock in the middle, which is what wait does to allow other threads to come and acquire it. Okay, good. Other questions? Okay, well, we have one more thing I want to look at today. I don't want to get into more, I guess we lost our notes, but what we were going to look at is something called the reader-writer lock. And we'll spend a little bit of time figuring this one out. But let's first understand what it is. The reader-writer lock was created because people realized that sometimes there's some different usages for some different ways data structures are accessed concurrently. And that in some cases we can get more concurrency by recognizing those differences. In particular, some threads might be what we call readers, and some threads might be what we call writers. And of course, a given thread may actually act as a reader at some point and as a writer at a different point. And a reader means we just read the data structure of interest. And a writer just means that we actually write, or what we might call update, the data structure. And so we're trying to use, we know that when we have threads and they're accessing a data structure concurrently, we have to think about concurrency a little bit. But really where we only need to think about that is in the case where there's writers, right? Critical section, the definition of that is basically some piece of code that updates or writes to a shared data structure, right? The key phrase there being update. If you just had a value sitting in memory, a counter value, but nobody was incrementing it, every thread could clearly just read it. You don't have to do any locking then, right? You would just read it. If you knew everybody was just reading, there would be no interesting concurrency problems. It's changing values, changing a counter, something as simple as that, changing something more complicated, like a B tree. Like if you take the database class, 564, who's taken 564? A few of you. Who's going to take it? Some of you. Who's taking it right now? So anybody taking it right now? A few of you. I'm sure you talk a lot about B trees in there. That's a complicated data structure, and figuring out how to update it concurrently is interesting and challenging. But it's the updates that are challenging. If you just had a fixed B tree in memory and everybody was reading it, nothing that interesting, right? Of course, many threads could read it at the same time, and there would be nothing incorrect about that ever. Okay, so given that, what people came up with was something we call a reader-writer lock, and it has this exact property. Okay, the lock is going to do this. It's going to we're going to acquire it when we want to read or write, but we're going to basically have two different kinds of lock and unlock statements. So we have a read. We can do a read lock acquire and a read lock release, or we can do a write lock acquire, and a write lock release. So if you're just going to go read it, you're going to call these read lock acquire and release around the critical section. If you're going to update it, you call write lock acquire and release. So this is to update, this is to read. And then this is the property that the lock is going to try to maintain. The property of a read-write lock is very simple. It's that either we'll have n concurrent readers, so we're going to allow many readers into the critical section, or we can allow one writer, but not both. So this is what you would call exclusive or, right? One or the other, but not both. We often say or in the non-exclusive way in English or colloquial terms. Here we mean XOR, right? N concurrent readers, XOR, one writer. We want one or the other, but not both. Does that make sense? So this is what we're going to allow. This is the property we're trying to maintain. We're trying to build a lock that has this property. Readers call read, acquire, and read release around that critical section, and writers do the same through a slightly different routine. Okay? So what we're going to do now, let me first ask, are there any questions about that? Does that make sense? Okay, good. So what we're going to do now is stare at some slightly more complicated code, which is actually a simple implementation of a read-write lock using semaphores. Okay, so it's from a very famous early paper called Reader-Writer Locks Using Semaphores, or something like that. I don't remember the exact title. And let me just go here. Okay, and this kind of fits on the screen. This is really squished, so let me spread it out a little bit. I guess we have a little bit more room. Not that much. So this gets the entire reader-writer lock onto the screen. Let me explain a few pieces of it, and then I'm going to let you puzzle through the rest of it on your own, trying to reason through what it does. So we're going to declare this read lock type. I was asked a moment ago, why do we always put underscore T? That's just a convention that people have used in the world of C for a long time to indicate this is a type. So is that a good convention? I don't know, but that's just one that's used. So inside of this read-write lock, this reader-writer lock, we're going to have two semaphores. One we call write lock, another we just call lock, and then we have an integer counter which is called readers, which we're going to use to track how many readers are in a critical section. So we call init once, and that's this code here, squished into this, just into this little space right here. And then you can see two sets of routines here. Read lock, acquire the read lock, release the read lock, and then acquire the write lock, release the write lock. So readers call these two routines, and writers call these two routines. And the important thing is that what I'm claiming here is that the code is trying to obey that property of either allowing many readers in or one writer, but never both. We don't ever be the case where there's readers running in the critical section and there is a writer and they're changing it while they're reading it. Okay? That's just what we're trying to achieve. So what I'm going to let you do is just stare at this for, let's say, 3 minutes while I force you to listen to some more symphonic music. So why not? Trying to pick a good one. Well, you all know the fifth, undoubtedly, so let's not do that. Let's do some really sad music. All right. It's pretty quiet. It'll build up. Nice. It's kind of almost like a funeral march. So this I'll definitely play during the exam. Building to a crescendo, as is your understanding of this code. This part is so awesome, I'm going to let it play. All right. Which symphony is that? Who knows? Anybody know? What if I said you get an A+ in the chorus if you know? Would anyone guess? But if I say if you get it wrong, then you get an F. I should have told you that first, probably. It's the 7th symphony. Think about that. Music written, 200 years ago, right? You always think of progress. It's like everything gets better, but nobody can write music like that anymore. It's actually quite sad. So in any case, that's the 7th symphony. Quite an awesome symphony as well. Okay, so let's try to figure out this code a little bit. We can see that, well, we're going to use this counter here to account for the number of readers that are active if there are readers in the critical section. So of course we're going to start it out at 0. And then you can see we initialize both the lock and the write lock, well, in what way? As if they are like they're binary semaphores, right? In other words, they're going to act as locks, as mutual exclusion primitives. So it's just like having a lock. So then all we have to understand is how those locks are called to make sense of this code. We have, if we're looking for just that plain old lock, you can see it's acquired and released at the beginning of the read lock acquire code, and it's also acquired and released at the beginning and end of the read lock release code. Okay? So it's clearly just kind of protecting this as a critical section. Whatever's inside this read lock acquire and release code, that's what that lock is doing. It's just making sure that we do those things atomically. Okay? That makes sense? Then I'm going to look at the write lock and how it's used. And you can see the write lock is actually used in a few different places. And so we have to understand its interplay to make sense of this lock fully. It's kind of easiest to understand, I would say, if we just use this as a write lock, it'd be pretty obvious why it works. We only want to allow one writer into a critical section. When they want to go into a critical section, they call acquire the write lock, and they simply acquire that lock by waiting on the write lock. And when they're done with that critical section, they release the write lock by releasing it here. So that's easy. Let's see what happens when readers, let's say there's nobody owns a lock right now, no reader or writer owns a lock at a given time. Let's say a reader comes in. A reader comes in, it grabs this lock because it's available, and then it increments this value. It says now there used to be 0 readers in the critical section, but now there's about to be 1. And then it does something that only the first reader into the critical section is going to do, which is it attempts to acquire the write lock. Okay, so it attempts to acquire the write lock. Let's say it does acquire the write lock. Then it releases this other lock, the main lock that we use to protect the code inside of this here and here. So now, what do we know is going to be true? As long as this reader is in the critical section, what do we know is true at that point? The write lock is locked, which means that if a writer comes in and tries to enter the critical section, it'll try to acquire this lock, right? But it won't be able to. So clearly, that first reader is going to be the one that ends up preventing any, by grabbing the write lock, it prevents any writer from then entering the critical section. Now let's say that reader is in the critical section and another reader comes along. What's going to happen? Sorry? Well, does it? Remember, the first reader, let's say, called acquire read lock. It locked this. It incremented readers to 1. It says, is readers 1? Yes. It acquired the write lock. And then it released the lock, this lock, right? So the next one comes in. What's it going to do? Is it going to be able to acquire this lock? Yeah, it is, right? Which is good because we want to let multiple readers into the critical section. It's going to increment readers from that point, and readers, of course, is, that's what this lock is protecting. It's making sure we can increment readers and examine its value without worrying about intervening updates or changes to the value. So the second reader to come in is going to increment it to 2. And then it's going to say, is readers equal to 1? And it says no, which is good because if it tried to acquire the write lock, what would happen? It would get stuck. Right? We don't want multiple readers, the second reader to get stuck. We want it to go through. So it won't try to do this. It'll then release this lock. and now we can have 2 readers in the critical section. Okay? And of course we could have 3 readers and 4 readers and 5. At some point, let's say we had 5 readers, they start coming out of this critical section. We had 5 enter at about the same time. They're all in the critical section at the same time. Let's think about what happens. The first one comes in, it grabs this lock. Is it able to? Yes, because that lock isn't generally held except when somebody's acquiring or releasing. So we're able to get this. We decrement the number of readers from 5 to 4. We check, is it 0? It's not. So then we just release this lock. The next reader comes in, it releases it, goes from 4 to 3, from 3 to 2, from 2 to 1, and then here's the key transition now, is the last one out. So when we go from readers 1 to readers 0, it says, oh, I'm the last reader out of this critical section. I'm going to release the right lock. Sorry about that. By the way, isn't it that whole chair moving around thing stopped happening, right? Yeah, that's because I found the person and I took care of it. No, that's not true. So anyway, last reader out is the one that lets go of the right lock. First reader in grabs the right lock. Last reader out releases the right lock, and now a writer could again acquire the lock, or some other future reader could acquire it at that point as well. Okay, so does that flow make sense? Now how about this case? What if we're enter the read lock, we grab this lock, okay, this lock over here. Is it ever possible for a reader to get stuck here, waiting for the right lock? Does the question make sense? Reader grabs that, the lock called lock, and then it's trying to acquire the lock called right lock. Can it get stuck trying to acquire the lock called right lock? Yeah. Yeah, exactly. So if a writer had first grabbed the right lock and is in the critical section updating the data structure, of course a reader could come in and grab this lock, succeed, and then get stuck waiting here. Okay, and that's totally okay. Now here's a question. Let's say another reader tries to come in at that point. What will it do? Yeah, it'll get stuck up here, right? It'll get stuck waiting to acquire this lock, and that's totally okay too. But you should just notice there's different cases where a reader can get stuck. It could get stuck, of course, trying to acquire this main lock that protects this critical section. It could also get stuck on this right lock while holding this other lock. That's okay. It just means other readers in the meanwhile will get stuck before they even could get into this code in general. So that's a little bit about how a reader-writer lock works. This is a pretty simple implementation, and simple usually means, well, working, but maybe not perfect. And when you look at a lock like this, you should, at this point, be developing a little bit of an intuition about, hey, there's something about this that's bugging me. So what about this implementation is bugging you? What do you think is maybe a problem with this implementation of reader-writer locks? It's just like what, 12, 15 lines of code. Yeah. Yeah, it's a writer starvation. You've heard of starving writers, right? That's not from this. So in any case, sorry, bad jokes included. In any case, a writer, you notice once a reader gets into the critical section, as long as there's a steady stream of readers, they'll keep getting in, and they'll increment and decrement the reader value. But as long as there's one reader in there, you're kind of stuck. You never can guarantee that a writer will get to update the data structure. So under heavy contention with lots of readers, writers get starved. And that's just a property of this implementation. There are much more complicated implementations that try to deal with that. You can probably imagine how, but they're pretty hard to understand. So that's Semaphores. We'll talk a little bit more about Semaphores next week. Otherwise, have a good weekend, work on your projects, and see you. And I have an office hour at 11.